Yo, what's up, guys? Welcome back to another video. And today we're going to be talking about an introduction to thermodynamics. And we're going to be using the equation that you probably might heard of before, the MCAT. It's not a literal cat. It's not even supposed to be spelled like that. It's not MCAT. It's M with the change of T, MCAT. With the change of T times the heat capacity. So I kind of spelled it wrong, but it looks like that. So essentially, what thermodynamics is just the laws stating how heat flows and how heat works in general. And so I'm not very too knowledgeable on this subject, like PhDs and masters and your old physicists, but I think I'm good enough to say that I know that the basics, the introductory basics, and I'm able to explain it to someone. Because the laws of thermodynamics get very hard and very quickly. But here's my interpretation of the four laws. People might say there's only three. There's four laws symbolically, and then some equations. So let's get into it. Let's put a little bit red. The first law: energy energy is never lost. And energy is never lost. It's such a bad term. But here's what I mean. Energy can only be transferred. It can never be created or destroyed. And so that's led to me, and so with this first law, it's already led to me being like, oh, well, how did the universe come about then if energy can be, destroyed or created? And honestly, I don't have the answer to that, so don't ask me. But oh my god, who's getting robbed? But essentially, energy can never be created, destroyed. It can only be transferred. And here's what I mean. Let's say, and I think it's better if I explain it with this equation. So what this equation means is just the flow of internal energy of a system, which is equal to the heat minus the work. Here's what I mean. So let's say you had a system. A system is essentially just an object, like a human, like a cup, like a machine that could be, a system. Essentially, what this equation is saying is that there always has to be some sort of energy being transferred through other ways of energy. If you recall in pre-calculus or even in your physics classes, let's say you were on top of a high building and you had a ball. If you were to drop this ball, you're not going to get it all the way back. Simply because it's not possible in the realm of real world. You always lose some of that energy, some of that potential energy, because then it becomes kinetic energy, but then some of that energy, when it hits the ground, it could be lost to sound. It could make an impact that could also lose energy. It just loses energy. Essentially, where that energy has to go is it has to go into the ground, since that is the system gaining energy from another system. Here's what I mean. Let's say you had a machine, right? Say you had a machine. And essentially, if you were to give this machine 500 joules, 500 joules of energy, and it was to make or create something or whatever, that 500 joules of energy is being transferred to whatever it's making. The reason why that is because work is being done by the system. So let's say the machine had an internal energy, or let's say it had like heat of 1,000. And let's say it takes about 500 joules to create something. Essentially, you can use this equation, internal energy is equal to heat minus work. So let's say that it had a heat of 1,000 joules, and then it used 500 joules of work. Essentially, the change of the internal energy is going to be equal to 500 joules. Because because it's not about how much energy it is, but how much energy you're transferring. That's essentially what the first law is saying. The second law is saying that entropy always increases naturally. And you might be wondering, well, what is that? Well, honestly, I have no idea. Entropy to me never made any sense. But the best thing I can tell you is that I had an example of a question. And it was like, let's say you had the Arctic tundra. It's cold, it's like dry, there's no sun. Well, there might be sun, but it's like cold and dry. But the interesting thing is that water still evaporates from the Arctic tundra. So what that means is that there's still enough energy in the system, which is the Earth, to make these water droplets evaporate, even in a cold and hellish place like the Arctic tundra. And I've been remembering that example, and it's been, and what I attribute to is that you can always have more energy than you started with. Or essentially, you're never going to go back to the same place that you were before. Because even in Antarctica, you can still have evaporation happening. You still have phase changes happening. It's not just going to stop because you're in a cold place. It's going to continue always. And so that's what I mean by entropy increases naturally. Number 3. As a system goes to 0, as a system goes to 0 in temperature, or absolute 0, it reaches near absolute 0 but never goes to it. So essentially, you can never take all the energy out of something. We've tried it before, and humans, we've made so many cold temperatures. We've been close to absolute 0, but we can never be at absolute 0, simply because there's always going to be some sort of energy that remains, and it's impossible to reach absolute 0. Because you can't have a state of nothingness. That's essentially what it is. You can't have a state of no energy, because there always has to be something there left. And it actually ties back to the second law, entropy increases naturally. Because you always need to have something there. And if you're wondering, absolute 0 is equal to like negative 273.15 degrees Celsius. This is when Kelvin is equal to 0. Lord Kelvin was just some dude, came up with some temperature. It's pretty cool, dude. Symbolically, these are the 3 laws, but there's also a 4th law. It states that within the system, let's say you had A as a system and B. Let's say that the heat of A and B, or the temperature or whatever, the energy, is equal, A is equal to B. Then let's say you had another system of C. If B was to equal C, therefore A is equal to C. And this is essentially like a little equilibrium. Essentially, what this means is that heat never flowed anywhere. It just stayed the same. And so if you had one thing equaling to another, and that thing equals to another, then everything has to be equal. You can't have any changes because then this will break apart. If B wasn't equal to A, then you couldn't say that A was equal to C. But since everything is equal, you can say that everything is equal. So this is symbolically like the fourth law. So I'm gonna just put like a little asterisk. And so let's go into what MCAT really is. And so you might be wondering, what is MCAT? Well, MCAT in short, it's just a math equation that states energy. And so you might be wondering, we might get back to the U is equal to Q minus W. What I'm going to be talking about now is this equation. M times C times triangle of T, delta T, whatever you want to say. Essentially, we're going to be talking about this dude now. This is heat added to a system. And you might be wondering, well, how can we find that heat? Perfect. Here's your equation. Essentially, we have MCAT. MCAT, what it essentially stands for, is just for the heat added to a system, or just heat in general, is mass times the heat capacity times the change in temperature. And so you might be a little bit confused as to why this matters, but symbolically, let's see what this represents. So since we know heat, or heat added, whatever, is equal to mass times heat capacity times change in temperature, mass is essentially just weighed out in grams. Heat capacity is actually weighed out in joules over grams degrees Celsius, I believe. Yes. And then change in temperature is obviously Celsius, Kelvin, whatever you want to make it to. But usually in chemistry or in physics, whenever you want to use it, we typically use Celsius when we're given it. So I'm going to use Celsius. Essentially, just take a look at this. Q is equal to MCAT. Now, I'm going to explain delta T before we get into any calculations. Delta T essentially means the change in temperature. What delta T also represents is the change in the final temperature minus the change of the initial temperature. This is another way to represent delta T, because delta is just a symbol for change. And essentially, if we had, let's say we had like a 99 degrees Celsius as our final temperature. TF is just final temperature. And our initial temperature was 81 degrees Celsius. Essentially, we would be given 99 degrees minus 81 degrees Celsius, which would be a change in temperature. Let me see if I could do simple math. 18 degrees Celsius. Essentially, what this means is that we're going to get a positive value in terms of heat, because if we get a positive value of the change in temperature, that means heat was added to the system. Because in order to make something hotter, you have to add heat to it. You have to add energy to it. So essentially, this is just kind of a way to think about delta T. It sounds obvious, like, yeah, you have to heat it up. Like, I have to make my pasta. Yeah. But, like, it makes more sense symbolically when you see it, like, down on paper and you have to write it down. It makes more sense that way. And something else I wanted to talk about was how if you have a greater mass, then the heat required is more. So I just found that interesting. Because obviously, if you have like 100 grams of water versus 1 kilogram of water, you're going to need a lot more heat to heat up that pasta if you have 1 kilogram of water. But then again, who is cooking real pasta with 1 kilogram of water? I don't know. Let's get into some equations. So we have Q equals MCAT. So let's just write this down. So, I forgot to explain C. C is essentially heat capacity. And heat capacity is another way of saying how much energy to raise temperature by 1 degree Celsius or Kelvin. And I forgot the number for like a lot of other metals, but for water it's 4.184 joules over grams degrees Celsius. And as you go on into thermodynamics, you can see that water has a very, very high heat capacity. Reason why that is because of the special, abilities and stuff like hydrogen bonding. But you can see that a lot of metals. Let me search one up real quick. Let me search up what was it? Heat capacity of Fe. Why not? So the heat capacity of Fe or iron is 0.45 joules over grams degrees Celsius. So you can see how it takes significantly more energy to heat up water than it is iron. And I would attribute that because it's a metal. That's just my personal definition. But let's get into some calculations. So let's say you had, and we're going to use both examples. Let's say you had, first off, you had water. So let's say you had a mass of 10 grams of water. Then the specific heat capacity, you can just write all these down, is 4.184 joules over grams degrees Celsius. And let's say, since this is a liquid, let's say you was to warm up this water from, I don't know. Let's say you change it by 50 degrees Celsius. Why not? So essentially, to use this equation, you just plug everything in. But since this is involving a lot of constants and like things that cancel out, you have to include your variables here. You cannot just go in blindly and not put your variables and stuff. Like, you always gotta put your grams, your little joules, grams, degrees Celsius, because it's like, this is what I mean. So look, once we put everything into Q, we have 10 grams times 4.184 joules over grams degrees Celsius times 50 degrees Celsius. And essentially from here, we can just cancel out the grams, cancel out the Celsius, and we're left with joules. So now all we have is just 4.184 joules times 50. Because we cancel out all the, the constants and stuff. Not constants, I forgot what the name was. So now let's put this into a calculator. And I don't have every single value ready. 10 times 4.184 times 50. So the energy needed to heat this up is 2,092 joules. If you want to convert this to kilojoules, we can do that too. So what it essentially means is that in order to heat up a sample of 10 grams of water, and then you wanted to heat it up with the temperature changing to 50 degrees Celsius, because it's not negative, we're adding energy to it. So this means that we need 2.092 kilojoules of energy in order to make that happen. And so here's what I mean. Let's take the same example, but with iron this time. So we have a mass of 10 grams of iron. So I'm going to put Fe here. And then the heat capacity of iron, we said before, was 0.45 joules over grams degrees Celsius. Then let's have the same temperature change. Why not? It's equal to 50 degrees Celsius. From here, we plug everything in. Don't forget your constants or variables. I forgot what the name was. I really forgot what the name was. You can see where everything is about the same except for the heat capacity. So when you cancel out degrees Celsius, then you cancel out grams. So Q would be 10 times 0.45 joules times 50, which is 10 times 0.45 times 50. And you get a total heat of 225 joules. Now let's change that to kilojoules to really see the amount of energy being added. So then your total energy, in order for that to happen, is 0.225 kilojoules. And reminder, this isn't a perfect system. This is if you somehow got all the energy to stay within that 10-gram sample of each element or each compound, and you were not to lose energy due to the sample that you have, like a cup, like energy somewhere. You can see how it takes vastly more energy to heat up water than it is iron. And this is why when you're making pasta, it takes so long for the water to boil. I was boiling pasta like a few weeks ago. It took me forever to boil. It was so annoying. But essentially, this is just a way to find the heat needed in order for something to be heated up to a specific temperature change. And you can see that even though these are just 10-gram samples, you can see that for some compounds, it takes a lot of energy in order to heat up something. And it's just, I don't know, I just like seeing the difference in energy. I think there's a thing called a calorimeter, something like that. It takes like 900 kilojoules to boil up, something like that. I forgot. But essentially, this is the basis of thermodynamics. I try my best to explain it. Hopefully, I helped some of y'all out. This is just my interpretation of it, though. If I did something wrong, if I made my numbers wrong, if I did something wrong, just leave it in the comments. Essentially, this has been an intro to thermodynamics. And just like what it is exactly. It's just energy, and it's just really annoying and scary and hard. But I know y'all can do it. Thank you for watching. Please like, share, subscribe. Very, very important. But this has been an intro to thermodynamics. Thank you for watching, and goodbye.